So we continue to talk about proteins. Proteins are linear polymers formed by linking the alpha carboxy group of one amino acid to the alpha amino group of another amino acid. This type of linkage is called a peptide bond or an amide bond. So the formation of a dipeptide from two amino acids is accompanied by the loss of a water molecule. The equilibrium of this reaction lies on the side of hydrolysis rather than synthesis under most conditions. Hence, the biosynthesis of peptide bonds requires an input of a free energy. Nonetheless, peptide bonds are quite stable kinetically because the rate of hydrolysis is extremely slow. A series of amino acids joined by peptide bonds form a polypeptide chain. And each amino acid unit in a polypeptide chain is called a residue. A polypeptide chain has directionality because its ends are different. An alpha amino group is present at one end and an alpha carboxy group at the other. The amino end is taken to be the beginning of a polypeptide chain. By convention, this sequence of amino acids in a polypeptide chain is written starting with the amino terminal residue. So as the illustration of the pentapeptide YGGFL shows the sequence from the amino terminus to the carboxy terminus. For example, this pentapeptide we call the leucine acetylphenone is an opioid peptide that modulates the perception of pain. The reverse pentapeptide, like LFGGY, is a totally different molecule and has no such effects. A polypeptide chain consists of a regularly repeating part called the main chain or backbone and a variable part comprising the distinctive side chains. The polypeptide backbone is rich in hydrogen bonding potential. Each residue contains a carboxy group, which is a good hydrogen bond acceptor, and with the exception of proline, an NH group, which is a good hydrogen bond donor. These groups interact with each other and with the functional groups from one-side chains to stabilize particular structures. In some proteins, the linear polypeptide chain is cross-linked. So the most common cross-links are disulfide bonds formed by the oxidation of a pair of cysteine residues. The resulting unit of two linked cysteine is called cysteine. Extracellular proteins often have several disulfide bonds, whereas intracellular proteins usually lack them. Rarely, non-disulfide cross-links derived from other side chains are present in proteins. For example, collagen fibers in connective tissue are strength-ended in this way. In 1953, Friedrich Sanger determined the amino acid sequence of insulin, a protein hormone. This work is a landmark in biochemistry because it showed for the first time that a protein has a precisely defined amino acid sequence consisting only of L amino acids linked by peptide bonds. This accomplishment stimulates other scientists to carry out sequence studies of a wide variety of proteins. And currently, the complete amino acid sequences of more than 2 million proteins are known. The striking fact is that each protein has a unique, precisely defined amino acid sequences. The amino acid sequence of a protein is referred to as its primary structure. Examination of the geometry of a protein backbone reveals several important figures. So first, the peptide bond is essentially planar. So thus, for a pair of amino acids linked by a peptide bond, so 6 items lie in the same plane. So the alpha carbon atom and the CO group of the first amino acid and the NH group and the alpha carbon atom of the second amino acid. The nature of the chemical bonding within a peptide accounts for the bond's planarity. The bond resonance between a single bond and a double bond. Because of this partial double bond character, rotation about this bond is prevented and thus conformation of the peptide backbone is constrained. Two configurations are possible for a planar peptide bond. In the trans configurations, the 2 alpha carbon atoms are on opposite sides of the peptide bond. In the cis configuration, these groups are on the same side of the peptide bond. Almost all peptide bonds in proteins are trans. This preference for trans over cis can be explained by the fact that steric clashes between groups attached to the alpha carbon atoms hinder the formation of the cis configuration, but do not arise in the trans configuration. By far, the most common cis-peptide bonds are X-pro linkage. Such bonds show less preference for the trans configuration because the nitrogen of proline is bonded to 2 tetrahedral carbon atoms, limiting the steric differences between the trans and cis forms. In 1951, Linus Pauling and Robert Corey proposed 2 periodic structures called the alpha helix and the beta pleated sheet. The first of their proposed structures, the alpha helix, is a rod-like structure. A tightly coiled backbone forms the inner part of the rod, and the side chains extend outward in a helical area. The alpha helix is stabilized by hydrogen bonds between the NH group and CO groups of the main chain. In particular, the CO group of each amino acid forms a hydrogen bond with the NH group of the amino acid that is situated 4 residues ahead in the sequence. Thus, except for amino acids near the ends of an alpha helix, all the main chain CO and NH groups are hydrogen bonded. Each residue is related to the next one by a rise, also called a translation, of 1.5 angstrom along the helix axis and a rotation of 100 degrees, which gives 3.6 amino acid residues per turn of helix. So the pitch of the alpha helix is the length of one complete turn along the helix axis and is equal to the product of the rise and the number of the residues per turns, or 5.4 angstrom. So the screw sense of an alpha helix can be right-handed, we call it like clockwise, or left-handed, it's like counterclockwise. So the Ramachandran plot reveals that both the right-handed and the left-handed helix are among allowed conformations. However, right-handed helix are genetically more favorable because there is less steric clash between the side chains and the backbone. Essentially, all alpha helix found in proteins are right-handed. Okay, so in schematic representations of proteins, Alpha helix are deciphered as twisted ribbons or rods. The alpha helix content of proteins ranges widely from none to almost 100%. For example, about 75% of the residue in ferritin is a protein that helps store iron or in alpha helix. Indeed, about 25% of all soluble proteins are composed of a helix connected by loops and turns of the polypeptide chain. So single alpha helix are usually less than 45 angstrom long. So many proteins that span biological membranes also contain alpha helix. Okay, so that's all for today. Thank you for listening.